So it says in your book, in pages before, like I don't know, from page 400 and above, it talks about the enthalpy of a solution. Okay, what I want you to understand about enthalpy, you have a table over there. That table could either be positive or negative. It can show you positive value or negative value. And the negative and positive have a specific purpose, definition, action. Okay, a positive enthalpy tells you that more energy is going to be absorbed, and a negative enthalpy tells you that more energy is going to be released. Like in the examples that we did for calorimetry, positive means absorption and negative means released. Okay? Now, in the first question it says, does the dissolution process is when you try to dissolve the solid, okay? Does the dissolution process absorb energy or release energy? So the first thing that you have to see to answer this question is analyze the sign of the enthalpy. Because the sign of the enthalpy is positive, means positive enthalpy, which also means that more energy is going to be absorbed. So when it says, does the dissolution process absorbs energy or release energy? So you have to answer that it absorbs energy. The reason is because of the positive sign. Okay? The reason because you have a positive sign. Now, in the other part says, as silver nitrate dissolves, how does the temperature of the solution change? So this is more about reading the paragraphs about the enthalpy. But to explain you better, think about kitchen gloves. Okay? Think about kitchen gloves. I'm going to put an image to explain this part. So, whenever I need to take out something that is baking from the oven, I use kitchen gloves. The reason is for safety. Okay, I don't want to be that my hands get burned. Okay, so I use gloves. Pretty simple concept. I bet that you do something similar than me. Now, what happens with the gloves? The gloves have one characteristic. Gloves absorb energy. Okay, that's why you don't get burned. Okay, so here the gloves help you to cool down. Okay, your hands are not going to get burned, plus the baking pan, it's going to cool down. So from this idea, I want you to analyze this question in part B. It says, as silver nitrate dissolves, remember it has a positive enthalpy, which means that it absorbs energy. How does the temperature of the solution change? So in the end, the silver nitrate is going to be dissolved, okay? So energy will be absorbed. And when that happens, the solution is going to cool down. In other words, the temperature is going to be, it's also going to be reduced. And when this happens, when an object cools down or the temperature is lowered, how does that going to affect the dissolution process? Remember, the dissolution process is how quickly the solute dissolves, okay? So, if the temperature is low, how do you think is going to be the dissolution process? Is it going to take more time because it has less temperature? Or is it going to take more time because it has less temperature. Remember, in the presentation I showed you factors that affect the rate of dissolution. Heat, okay, heat affects the dissolution process. So, if you want to dissolve sugar in cold water, it's going to take more time to do it than if you do it with hot water, okay? So, temperature affects positively the dissolution process. The more temperature you have, the easier the solute is going to be dissolved. So right now here happens the opposite. The temperature goes down. If it goes down, then the dissolution process will take more time. It's going to take longer. The reason is there's not enough temperature to break down the particles of solute. That's the reason. And then it says, if the solution is heated, how will the rates of dissolution and crystallization be affected? So, remember, the silver nitrate with a positive enthalpy absorbs energy. Not much, just a part of the energy is going to be absorbed, okay? But if you begin to heat the solution of silver nitrate, the temperature will rise, okay? And if the temperature rises, then the dissolution is easier. It's going to take less time to do it. If it does, so the dissolution process will be faster. Why? Because more molecular energy makes the solute break down faster. That is the process, the internal process when you try to dissolve a solute. It is easier for a solute to dissolve in hot water, for example. And the reason is because you have more energy, more temperature represents more energy. And if you have more energy, you have more kinetic energy, which in the end gives you more molecular energy in general, and it is going to make the solute to break down faster and it's going to dissolve faster. That's the reason. So, in the end, how does the solubility of silver nitrate change after heating? The solubility tells you. Because now it's faster to dissolve the silver nitrate, we say that it becomes more soluble. As I told you, I'm not going to check this question, but I wanted you to understand what it is, how you interpret an enthalpy, okay? I don't know if you want to ask me something about this or not, since I'm not going to ask anything about it. But if you still have a doubt on this topic, on the exercise that I just explained, let me know. If not, I continue with today's explanation. Tick-tock, tick-tock.
Please continue with today's explanation.
Okay. So as we're talking about the dissolution process, remember what I told you in the last class, I guess? You can have two kinds of solids. You can have ionic solids, like salts, or you can have molecular solids, like sugar. Both behave differently, and that's why we have two kinds of electrolytes. We have electrolytes and non-electrolyte solids. The electrolyte solute are those that allow the electricity to pass through, okay? And the non-electrolytes don't help the electricity to go through. Now, why am I talking about it again? Because it is related. Everything is related. So this is chapter 13 that is called Compounds in Aqueous Solutions. So, Compounds in aqueous solutions. Solids, okay, can either be ionic or molecular. Ionic compounds form with cation and anions, and molecular compounds that are going to be made up of nonmetals. Okay, so in an ionic solid, a crystal structure is made up of charged particles held together by ionic attractions. Remember, the ions are either positive or negative, and opposite charges are going to be attracted. Those are what we know as ionic attractions. Think about ionic attractions like magnetism. Okay? Opposite poles get attracted. Okay? So in a molecular solid, molecules are composed of covalently bonded atoms. In covalent bond, um, what happens is that here they are sharing electrons, while in the ionic compounds they are giving electrons away. The solid is held together by non-covalent intermolecular forces. So I have two examples over there. I have octane, which is C8H18, and I have tin 4 sulfide, which is SN2S4, or simplified as SnS2. Tell me, octane, is it a molecular compound or is it ionic compound? Take a look at the composition of it. How is octane made up? What is carbon? Is it a metal or a non-metal? And what is hydrogen? Is it a metal or a non-metal? Carbon, where do you find it in the periodic table? In the metallic part or in the non-metallic part?
Both are non-metals.
Both are non-metals. Okay, both. Even though hydrogen is not placed in the part of the non-metals, hydrogen is a non-metal, okay? It's a gas. So, octane is what we know as a molecular compound or a covalent compound. But in the case of tin 4 sulfide, for example, tin is a metal, and metals, remember, they are like cations, and the non-metals are more like like anions. So in the end, when you have attraction of two ionic charges that are opposite, we say that this compound is ionic, while octane is going to be molecular or covalent. That's something that you already know so far. But let's talk about ionic and dissociation. When a compound that is made of ions dissolves in water, the ions separate from one another. This separation of ions that occurs when an ionic compound is dissolved is called dissociation. Remember the example that I gave you the other day. You have an amount of water and you add salt to it. What happens in the end? Salt, table salt, is known as an ionic compound, which is made of sodium and chlorine. Sodium, which acts positively like a cation, and chloride ion that works like an anion. So what happens when they are mixed with water? The ions separate. So what you have here is a crystal, okay? Sodium crystal, sodium chloride crystal. So when it's mixed with water, the particles, the ions, begin to break down, okay? They begin to separate. So my chlorine ion separates from my sodium ion, and then you have the ions charged traveling there in the water. They just travel in the water from one place to another, transmitting electricity. This process of separation, the separation of the ions, is known as dissociation. And I want to show you a dissociation example, but with a whiteboard, not here. Take a look to, I have two examples over there. The first one is the main example for a salt, okay? So we have sodium chloride, okay? And it says, okay, before we go into that, I want you to see what kind of reaction is this. Remember the type of reactions. So when you have a whole compound that separates, you have what we know as a decomposition, okay? But here we don't have elements. It looks like a decomposition reaction, but we don't have elements here. Okay? We have ions, positively charged ion and negatively charged ions. So take a look here. In dissociation, you're going to have a salt, okay, an ionic compound. So let's see the first one, sodium chloride. You know that sodium is a metal and it is located in the first group in the periodic table. So when you write the ionic form of sodium, it's going to be like that, sodium 1 plus. Now the other component that make up the sodium chloride is chlorine. Chlorine, the element, is diatomic, but when it is combined, it's called chloride, and the chloride ion has a charge of 1 negative. So when you form this compound, you will have the two elements joined together without charges and with the number of atoms. Remember that you have to change the charges, but in this case, because the charges are 1, you just ignore them. And in the end, this is the compound. But what I want you to see is this. What makes up the sodium chloride is actually the combination of two ions, positive and negative. So when this happens, okay, when this happens, you know that we have an ionic compound. Now, a dissociation example is how the salt is going to be, okay, so how the ions that form the salt are going to break down. So the way you do it, it's simple. To represent dissociation, all you have to do is write in the arrow, okay, the arrow that separates the original substance from the final substance, and you need to indicate H2O. H2O in this case means that sodium chloride is being dissolved in water. This is not a chemical reaction, okay? This is a dissociation example. So what I just did there tells you that sodium chloride is going to be dissolved in water. So what happens when sodium chloride is dissolved in water? The ions separate, okay? Okay, so the ions separate. So all you have to do is write in the ions. Cation comes first, and then the anion with its own charge. Now, here the indicator AQ for both is telling you that is dissolved in water. Okay? Aqueous, AQ means aqueous solution. So it means that it's already dissolved in water. You have sodium ion, but it's going to be dissolved in water. That's what AQ means. And the S for sodium chloride tells you that the initial substance that you had, it was a solid, okay? And it makes sense because if you think about it, the sodium chloride, the salt, are tiny little cubes, okay? So that's part of being a solid. That's how you do a dissociation example. Now, what about the second example? You have calcium chloride, solid, and you have an arrow with H2O indicator above it. That tells you that you have dissociation, okay? So, remember, calcium, in its ionic form, calcium has a charge of 2+. So all you have to do is it's doing like a backward process than in compound formation, okay? So all you have to do is write in the ions. You have calcium ions. Calcium is in the group 2, and all the elements that are in the group 2 have a charge of 2+. Then you will combine it with the other ion, that is chloride ion. And you know that chlorine is 1-. But here, as you can see, we need to do a procedure that you're already familiar with. You have to do a balancing procedure. The reason is because here you have 1 calcium and 2 chlorines. And in the product, as you can see, you have just 1 calcium and 1 chlorine. So you have to balance in it. So in order to balance it, you do a normal process. Just putting a 2 over there. Okay? Now your your chlorine is going to be balanced. And you don't forget to write the state of the substance. Calcium chloride is a salt, is solid. And the 2 ions, calcium ion and chlorine ion, they are going to be dissolved in water, so you have to indicate aqueous solution. As you can see, dissociation example is very simple. That's a very simple process. But you need to be aware that sometimes you will need to balance. Okay, go to your textbook in the page 413. Okay. Now, the dissociation equations that we just did are possible only when you understand the solubility rules. This table 1 is going to be useful for you to know if a compound is soluble in water or not. So let's analyze, okay? It says sodium, potassium, and ammonium compounds are soluble in water. So I'm going to write a compound here, okay? NaCl. Is it soluble? Is it soluble in water?
Yes.
The reason is because it has sodium, okay? So whenever you see a compound that is made of sodium, means that it's soluble in water, and also means that you can do the dissociation part. Now, it says nitrates, acetates, and chlorates are soluble. So, if you see a compound that has nitrate, acetate, or chloride, you have to say, okay, this is soluble. Then it says, most chlorides are soluble except those of silver, mercury, and lead. Lead 2 chloride, an exception of the rule, is soluble but only in hot water. Okay, so in this case, in the rule number 3, it tells you that most chlorides are soluble, but we have exceptions. Silver chloride is not soluble. Mercury 1 chloride is not soluble. Lead 1, not lead 1, lead 4 in this case is not going to be soluble, but lead 2 chloride will be soluble in water, but only in hot water. Okay? Now it says most sulfates are soluble except barium or barium sulfate, strontium sulfate, lead sulfate, calcium sulfate, and mercury sulfate. The rest of the sulfates are soluble. Most carbonates, phosphates, silicates are insoluble. Take a look, the rule number 5, it's been very specific about insolubility. So if I give you an equation that involves carbonates, phosphates, or silicates, the dissociation is not going to occur because they are not soluble in water. So what happens? Most are insoluble except sodium. Remember, compounds with sodium are soluble, so if you have sodium carbonate, even if carbonates are insoluble, the sodium is going to make it soluble. Potassium and ammonium, that are also part of the first rule. And then in the last rule it says, most sulfides are insoluble except those of calcium, strontium, sodium, potassium, and ammonium. This table, I'm not going to ask you to memorize it, but to keep it with you. Now, in the page 413, you have a practice that says, let me see, it says, if possible, write dissociation equations for the 6 compounds shown in the photograph. Otherwise, write no dissociation. Wait, I'm looking for the exercises here in the in my book. I don't have these exercises. Okay, just give me a second. I don't know why my book is different. I mean, my digital book. I know it's different, but I don't know why. I mean, I have almost everything right. So, let's see. Guys, what do you see? Do you see my presentation or the whiteboard?
Whiteboard.
Okay, good. So I'm going to work with you. I'm going to help you with the first two exercises. Okay? Let's take a look to the first one. Shut up. I totally hate Google. Every time I say okay, it looks for something. So let's see. The first one, that is nickel to chloride. What do you think? Is it going to be soluble or not? What does the rule says about chloride? The first one, nickel to chloride. The rule 3 says most chlorides are soluble except silver, mercury, lead. Nickel is not any of those elements, so is it going to be soluble or not? Is it soluble or not?
Yes, it's soluble.
Of course it's soluble. Gosh. Now, because it is soluble, you have to do the dissociation process, okay? Now, let's take a look to the second one. Potassium manganate, permanganate. Is it soluble? Yes or no? Potassium. Let's take a look at the rule. The rule doesn't specify anything about the permanganate or manganate itself, but it tells you about potassium. It says potassium compounds are soluble. So in this case, this potassium compound is also going to be soluble. And because it is soluble, means that we can do the dissociation equation. So you, as a homework, you will complete this table by writing